have to begin with some remarks on the philosophy of quantum theory. The approach I use is a pragmatic one. I don't feel I'm entitled to invent a philosophy. I look at the Hamiltonian and the action principle, or the best theory we have, which is the standard model, and I see it presents nature as a pattern of acts of creation and annihilation. And in fact, that idea has been pretty constant since the 1930s. It is in Wenzel's book on field theory, one of the first on quantum field theory. It hasn't gone away in the meantime. So I'm going to take that as a fairly stable aspect of physical theory for the future. The world is a pattern of acts of annihilation and creation. If you look into the history books, you find you have to go back a ways to find other philosophers who say this. The most conspicuous is a write-up by Maimonides in his Guide for the Perplexed, where he's describing the scholastic encyclopedia of Baghdad in the Middle Ages, which presents the world as a succession of acts of creation and annihilation by the divinity. Each instant, the entire world is created and, annihilated, and then a moment later created, and in between, things are filled with God. It's God who does the annihilation, the creation. So for this particular branch of Islam, atomism is extreme piety, which is very curious because in the Jewish tradition, Epicurus is another word for atheism. Okay, it's interesting. And anyway, my stupidity, my naivete is such that when I spoke on this general topic in Dubai, I thought I was honoring my hosts by mentioning the origin of this idea in Islam. And only recently I began to realize that in fact the Islamic scholastics are the extreme of heresy for the modern Islamic movement. You can't even find a reference to the Islamic encyclopedia online, not even at Amazon. I saw a copy of it myself at Yale many years ago, but I've never been able to find another. And so all I know about it is what I read from Rambam, from Maimonides, and other indirect sources. Okay then? I don't know why my computer has done that. It was my mistake to switch to the full screen mode. And the only way I know to get out of it is to turn it off and restart.
Turn it off at the top right hand corner.
Pardon?
Put your arrow right to the top right hand corner and you'll get the option to come out.
But then it doesn't stay out. So, for me, wave functions, rods with cats, represent acts of creation and annihilation. But I don't want that to sound too mystical, so I brought some along. And when this restarts, I can use it as a kit. Is this visible?
Yes.
Okay, this is the stream of photons, which it turns out are vertically polarized. Please visualize an arrow along the edge of this pointing upward, or downward, doesn't matter, to indicate the polarization. So this is a ket. This is a source of photons. And your eye combined with this polarizer form a rod, a detector of photons. And here, the transmission probability is as close to 100% as industry can make at a reasonable price. And then, as you rotate this, you see Born's law, which is actually Malus's law, discovered in 1804, that the transmission amplitude between two polarizers is the dot product of the brawn of the two kets involved. So here they're crossed and there's no transmission, and here they're parallel, and there is ideally 100% transition. To show the non-commutativity of quantum theory, I brought along another polarizer, which I'll use as a throughput, an operation. Where this is a vector, this will be used as a square matrix. And here they're aligned, and here they're crossed, nothing new. But here's something new, namely the order of these two is crucial. Crucial, that is. There you go. So this way you see a little light coming through, and this way it's still black. Okay, so I'm just commuting the two polarizers. So the non-commutative quantum theory is not something abstruse. It has to do with interchanging hardware. And Bronsted live on the interface. On the one hand, you can ascribe them on the hardware. You never, as Jacques pointed out, learn a Bronsted by looking at the quantum system. You look at the hardware, like this. But why on earth do you do that? It's because it gives you statistical information about the population of quanta produced by that hardware. So an oversimplification of the idea can be disastrous. It lives on the interface. There's 1 foot in the world of the experimenter, and the other huge number of feet in the world of the experimenter. And it has at least 1 foot in the world of the experimentee. It's a channel because it provides information about the system we're looking at. I consider what I've just done as operational. I carried out certain operations, so I'm sticking to this philosophy of operationalism, which is sometimes called merely instrumental. And it seems to me that merely is very indicative of the point of view of the speaker. Merely instrumental, it just keeps us alive. And it traces back to ancient Greece at least, where the instruments were left to the slaves, and the masters spent their time trying to know the universe, essentially by staring at their navels. The things that are most plausible to us are the things we learn when we're youngest, on the basis of the least amount of experimental information. So if something seems very plausible, we should immediately doubt it and check it with more modern, more recent data. Okay, then the actual problem of dealing with the infinite, I agree completely with the previous speaker who said there is no infinity in nature. Infinity is one of the actors in a beautiful drama with a highly refined, developed system of criticism called mathematics. It's an actor in that play as much as Macbeth is an actor in a play of Shakespeare. And so the question of whether infinity exists is for me the question of whether Macbeth really exists. And sometimes it's nice to say he does. Sometimes it's wiser to say he doesn't. Language is very flexible, both in physics, philosophy, and in art. We just have to keep account of all the possibilities and ramifications that we can. Okay, so to get rid of the infinities, let me go back to Albert, who at one point said, some have advocated, this is a rough quote, but pretty close, applying Heisenberg's algebraic method to space-time. But this is like breathing in empty space. That part I remember very well, because I agree completely. And I've been exercising my chest for the last 60 years, and I think I have a gasp of space that I can communicate to you. I won't go through the whole history, but a key point is rediscovering a paper that Irving Siegel wrote in 1952 or 3. He's a mathematician, not an operationalist. His book on relativistic quantum field theory doesn't mention an experiment. He's concerned with the algebras involved. And he pointed out that physics is evolving towards semi-simplicity. That's Siegel's principle. It's a guide for the evolution of physics. In special relativity, the evolution is from the Galilean group to the Lorentz group. Galileo is not semi-simple. It has this core of mutually commuting translations, first of all, but that's not that part of Galileo. And also the boosts, the velocities commute. And that means the killing form for that group is singular. It vanishes for all translations and all boosts. And that means the theory is unstable. The commutativity of velocities means certain commutators are zero. If you change that 0 to 10 to the minus 6, the resulting group is not isomorphic to the original one. The least change gives you a different group. This means that the assertion cannot possibly be verified by experiments, because experiments always have an error. The only Lie algebra that has a chance of expressing an experimental result is one where a slight error in the structure constants does not change the group, except for an automorphism. And the transition from Galileo to Lorentz stabilizes. Lorentz is semi-simple. Its killing form is non-singular, non-vanishing determinant. If you make a little change in the structure constants of Lorentz, it's still Lorentz looked at in a different frame. But on the other hand, Siegel points out, Poincaré is not semi-simple because of the translations. They commute like mad. You see, commutativity is suspect. It cannot be verified experimentally. The least departure from commutativity might escape our instruments, but it makes a totally different theory. And Yang, the story of quantizing space-time begins, of course, with Heisenberg. He had hardly finished quantizing the atom before he was quantizing space-time. It happens that Ivanenko and Oppenheimer were visiting him when he aired his speculations about quantum space-time. And so we have this paper by Ivanenko from Russia on the subject. And while Oppenheimer himself didn't work on it, he took the idea back to Princeton and told Hartmann Snyder about it. This is the Snyder-Oppenheimer team. And Snyder went off by himself and quantized space-time. It's the first paper with that title and subject matter that I know of. And Siegel looked at, Yang, C.N. Yang, still a graduate student, looked at Snyder's work on this, and so the group was pretty weird, pretty ugly. And just to make it simpler, he made it simple. He replaced the Poincaré Lie algebra and group by the only nearby Lie algebra that has the same number of dimensions, which happens to be the orthogonal group in 6 dimensions with one time-like dimension, which he held on to because that's the way it is in space-time. So it's SO51, or spin 51, is the Yang group for space-time. This is also called the conformal group, I believe. But that's not the right name for this group, because the conformal group just acts on the space-time coordinates, whereas the Yang group mixes space-time with energy momentum. In order to make the algebra of x, position, p, momentum, L, angular momentum, and I, the square root of -1, which appears in the commutation relations of Heisenberg. In order to make that Lie algebra simple, you have to mix everything. And the commutator of 2 p's is a rotation in Yang's theory. And then Siegel, perhaps rediscovering the Yang theory, points out that the resulting group is stable. Yang did it just for simplicity, just to make the group simple, and Yang points out that it's stable. And I'm going to build on their work today. I'm holding on to that group, but embedding it in a still bigger one because there's a lot more to physics than just space-time. So here are the main ideas of what I want to talk about. I've described operationalism. Now, another thing that George Ellis told us about is the importance of hierarchy in science in general. And I was so glad to hear that because I had only come to realize it myself very recently. I've been exposed to the idea since childhood. Korzybski coined the word multi-ordinal. I haven't found a synonym for it, so I'll use it. It means referring to many levels of abstraction at the same time. Quantum set theory is the main multi-ordinal algebra that we have in mathematics. It's used as a universal language, the lingua franca of first mathematics and therefore science today. So I'll have to present this structure, and it differs from the kind of tensor product algebra that has been discussed here many times, only having one additional operation, which creates the hierarchy. And this is the Cantor operation of bracing, which is used informally in all physics since the beginning of field theory. We say an electron is an elementary particle. This only means it has no parts. It certainly has elements. It has spin, it has position in space-time, it has isospin, it has generation number, and so on. You can think of all of these as modules which are assembled to make the electron. And then you have to brace them. Otherwise, if you have two electrons, they'll get scrambled. And this has been done since the beginning of field theory. It's just no one has written the braces. They write a symbol for the electron, and then they put two of the symbols together. The braces are left implicit. If you actually replaced the symbol for the electron by the product that it represents, then by commutativity, you wouldn't be able to tell one electron from the other. You wouldn't know which variables belong to one and which the other. So bracing, bracketing, what Dewey called unitization, but which I think had an older name in mathematics, association, goes on in every physical theory of any complexity, including Newton's, where you associate positions with times. He has to be, at least in his mind, bracing the combination to keep them together. I worry very much about the fact that I don't know how to do this in the laboratory. I, therefore, cannot slavishly hold on to my operationalism at this point. I have to pray that when I do enough physics with this, I'll establish the connection to laboratory operations, just as Dirac invented the gammas without really the foggiest notion of what one gamma means in the laboratory. And in fact, I'm not sure we have one yet, but the theory works beautifully. Okay, when I set up this algebra, it becomes a trivial remark, I'll expand on this when I get to it, that quantum sets are also spins. So making the world a quantum set is making it up out of spins. And that is not my idea. I first heard this from Penrose at our first meeting, when I told him about the black hole, and he told me about spin nets. And we had this exchange interaction. And so I'm returning to when I heard this again from Feynman, who expressed position coordinates as sums of a great many spin operators in 1937, while he was still a graduate student. And he asked me if I could understand why he didn't pursue that line of thought. Why did he drop the problem? And I didn't dare answer. So he told me, it's too hard. Okay. So I'm not as embarrassed as I should be at presenting this slight advance, which is thoroughly rooted in Feynman's suggestion of making the world up out of spins. If you think about it, what else in our experience could we make the world out of? The spin is, on the one hand, has the necessary transformation properties. On the other hand, we have the foggiest indication that it can be broken up into other things. And I've already mentioned my debt to Siegel. Okay. Some have tried to hold the word state in the transition from classical to quantum physics. For example, Robin Giles was the most beautiful exposition of operational or Bayesian quantum theory that I've seen in J-Math Phys in the 60s. You probably know his magnificent book on the mathematical foundations of thermodynamics, which is just beginning to get the recognition it deserves. And he had a similar paper on the foundations of quantum theory that really deserves more reading. And I think he uses the word state the way Randall and Fullis do, and some people here have, as the act of preparation. And Wigner in 1963 points out that the wave function that he calls a state vector has nothing to do with what's going on now, it's actions prepared in the past. But he still calls it the state. And inevitably, the less learned will assume that it's something you get by looking at the particle. In classical physics, we learn the state of a planet by looking at the planets. And I've tried to indicate here that you do not look at the photon to discover the cat vector that it came from. You can't tell what coach I arrived in Cambridge on by looking at me. You have to look at the coach. It's a creature of the interface. It brought me here and left a little trace of it on me. Okay, so I simply tune out when I hear the word state, unless I'm very, very aware that the speaker is using the modern language where the state is no longer a state. Remember, giving up the state is not giving up much. No one has ever seen one. It's entirely a creature of the imagination. No one's come close to knowing the state of any object we encounter. When you look at an apple, you see its skin. If you make an attempt to learn its state, it's no longer an apple. Okay, so this just recapitulates what I said with polarizers. In order to simplify, in order to get rid of all the singular groups, I have to get rid of the unitary group, the infinite dimensional group of a Hilbert space. So Hilbert space is wrong, that's all. A finite dimensional vector space has a chance of being right. But if you take a finite dimensional vector space, there's no chance, no way to represent the Lorentz group, for example. The Lorentz group is simple. We should hold on to that. It works so well. And therefore, Hilbert space must be wrong. The infinite dimensional is wrong because it's infinite, and the finite dimensional is wrong because it's compact and has no room for the Lorentz group in it. If you give away the metric, then its group becomes SL or GL, the linear group, which is not compact, and there's no problem at all in representing the Lorentz group. Dirac does it in 4 dimensions. But of course, it's not a unitary representation. The metric of Hilbert space represents a priori probability. And I think anything that's labeled a priori should light a warning sign. If your philosophy is experimental, there really is no a priori. You use what works. And that's what is based on earlier experience. A priori, we have nothing.
So could you just elaborate what you mean by a priori probability?
I'm sorry, there's 2 questions.
Could you just elaborate what you mean by this Hilbert space metric referred to?
If you want to compute, this is already presented by George. If you want to compute, if you want to compute the expectation value of, if you want to represent the probability distribution, you have to use a Hermitian matrix. Hermitian means commuting with the metric form of the Hilbert space. So, or let me put it more operational. Suppose you want to found Hilbert space theory on laboratory operations with inputs and outputs. It turns out if you just look at the forbidden transitions, that completely defines the linear structure. The path from the forbidden transitions to a numerical vector space is a path that was taken by the projected geometries of the 18th century from synthetic projected geometry to analytic projected geometry. The key idea is that of von Stauff, which introduces quadruples as a fundamental thing, which carries information in that all triples in the plane are the same projectively. To get something that means something, you have to communicate, you need a quadruple. And then the question, where did the metric come from? If you look at the assured transitions, then first of all, that determines the whole probability structure, and it also determines the concept of angle, which is what the metric expresses. So it's a distinction between the forbidden and the compulsory. And I'm taking the compulsory, the forbidden, as close to experience. It's much easier to disprove the assertion that a transition is forbidden, and if it happened once, then you know it wasn't forbidden. It's hard to prove that it's compulsory. It might happen the next time. It might not happen the next time you try. I guess it implies a relation to the stability criterion. And so I introduced Cantor's braces and Piano to make the system more algebraic. He was a great algebraicizer. Replaced the braces by an operator iota. Iota S is a unit set whose only element is S. And do with a unit closure. This is just to remind you that the idea of an element already occurs in physics implicitly. There should be electrons have no quarks, so they have elements. Then, in looking at the quantum theory, it's good to have classical roots. Let me remind you of the Cantor exclusion principle. Cantor said one set is either in another or it isn't. It can't be in it twice, and it can't be in it minus one times. Okay, so we call this the Cantor exclusion principle. And then we go over to quantum theory and discover that assemblies of electrons obey a similar principle that I will call the Pauli exclusion principle. And again, an electron can be in a collection of electrons either 0 times or once, but not twice, and slightly moved, whether it be in there minus 1 times. Is a positron just the absence of an electron? And I'm just going to take the position that Cantor was right. The positron isn't an electron. It's a different kind of particle. Now, that means that I'm restricting my language to things obeying the exclusion principle. That's great for electrons and muons and so on, but what about photons? And if I didn't have another principle to guide me in this dilemma, I would really be in trouble. Photons are supposed to obey Bose-Einstein statistics. The commutator of an annihilator in a crater is 1 for Bose statistics. That means that the algebra is not stable. The commutator of 1 with anything else is 0. Every time you see a 0 commutator, your ears light up. That Bose-Einstein must be wrong. Fermi-Dirac is good. Bose-Einstein is bad. I use it purely as technical terms to understand. It happens that Bose-Einstein has already been corrected. There's a significant Bulgarian physicist, Palev, Havdar Palev, who back in the 70s proposed to replace the Bose statistics by a simple Lie algebra. Bose is not even semi-simple because of that 1 on the right-hand side. He said the commutator of 2 elements is another element of the same kind. So, for example, the rotation group, the angular momentum commutation relations, could replace the Bose-Einstein commutation relations, provided you allow the possibility that one of the angular components of angular momentum can be centralized, can be made so big that there's a classical limit where it commutes with everything. So you can get back to Bose-Einstein from Palau in a singular limit. So I'm assuming, as Palau did, that the right statistics has, as Siegel would have if he had continued this line of thought, that Bose-Einstein statistics is a singular limit. That's why it takes an infinite dimensional Hilbert space to represent it. The right statistics can be represented in a rather small Hilbert space, like the rotation group. Okay, if you apply the operations of set multiplication, which is now the grasping product, and bracing, starting with a null set, you get a universe which is just like that of classical finite, totally finite, per finite sets, together with the operations of position. And here's a table showing the first few quantum sets. I hope I can enlarge it, but my computer is not permitting me. Maybe I can zoom. Can I do anything? Yes. On the wrong page. That can work. Forget it. I have to find that point. I got it. Thank you very much. Okay. Thank you. Okay. This looks a bit like a heat chain. The similar made by starting with number 1 for the empty set, the identity of this grasping algebra. And then whatever you've made, you can bar, that's putting it in braces, or you can juxtapose two things that you've made. That's the product. And here I've listed them by height, which is what von Neumann called the rank of the set, level of abstraction. Sometimes they call the order. And in each rank, I've assembled them by width, which counts the number of elements in the set, which in grasping algebra is called the grade. And this could have been done by Cantor. And to make it quantum, you just take superpositions. And remember that if you interchange two factors, you change the sign. So that if two of them repeat, it's 0. Yes?
Why the Grassmannian product?
Pardon?
Why the Grassmannian product?
PEP, the Pauli exclusion principle. Actually, because I do as I'm told. Classical set theory doesn't allow two things in the same set. Doesn't allow one thing twice in the set. So I wanted to make a quantum set theory. Who am I to argue with Cantor? And then it just happens to fit the Pauli exclusion principle. So I grasped it even more firmly. to the extent that I'm going to try to make all the bosons out of even numbers of these fermions. And that goes for space-time too, which is bosonic because of the Heisenberg commutation relations, which are just those of boson sensitistics. So a space-time point has to be an even assembly of pairs. And those give us the atoms of space-time. So the width is called the grade and the height is called the rank. And if you look at the way the numbers go, it's 1, 2, 4, 16, 64K. Those are all still within the human realm. And the next step is the big one, be careful. It's 2 to the 64K, which is a number much bigger than anyone needs in a physical theory. So even though at this point we're totally ignorant about the microstructure of nature, we can be almost certain that the break between the microscopic and the macroscopic occurs in the transition from rank 4 to rank 5. Rank 4 is ridiculously small for field theory. Rank 5 is ridiculously large for empirical field theory. Okay, then let me show you that all these creatures are actually spins. First of all, each rank is a Grassmann algebra in its own right, closed under multiplication by construction. And then, if you look at the linear operators in the Grassmann algebra, the variables of a quantum system of a certain rank, they can easily be written in terms of left multiplication by an element of the Grassmann algebra, which is a creation operator, put something into the set, or differentiation with respect to an element, which takes something out of the set, operations of creation and annihilation. And those are Fermi-Dirac operators of creation and annihilation. They obey the Fermi-Dirac anti-commutation relations, which are incidentally a Clifford algebra. Okay, so the observables of a quantum set form a Clifford algebra. That's the first thing. Then the Clifford algebra is represented and operated on the Grassmann algebra. But what a Clifford algebra acts on is called a spinor space. So every Grassmann algebra is a spinor space. And the spin operators are linear combinations of the usual operators of creation and annihilation for a Fermi-Dirac ensemble. The Dirac gammas create and annihilate something. The spin operators are creators and annihilators of something that I'll call pre-spins. I'll use the word pre in general for the elements of a set that we made this way. There must be pre-spins, of which spins are assemblies. Now, here comes some numerology. I wish I had something as convincing as the Balmer series, or the Rydberg formula. But there is so little connection to experiment so far that I really have to grasp at straws. And one straw is that if you look at the sequence of dimensions of the ranks, it's 1, 2, 4, 16. And each is built up of the early ones. So 16 is presented as 1 for rank 0, then 1, 1 make 2 for rank 1, plus 2 gives you rank 2, and then 12 more gives you rank 3. Okay. These happen to be the distribution of kinds of fermion. There are 16 basic fermions. And here are the quarks, and here are the leptons. And these are presumably the electrons, and these are the two neutrinos. This one is crucial. Fortunately, the right-handed neutrino seems to exist. Here, let me set it in words. And I'll use this as a guide in interpreting this algebra, because I don't have much.
That does not include 3 families.
Pardon?
That does not include three generations.
Uh, Since I haven't solved that problem, let me put it off till later. I will speculate about it. I hope I won't have the time to do that.
That's okay. If you find a third of the universe, that's good enough.
Okay, let me do it now then. Okay, I put myself in the hole, I have to. One thing we know about generation changes is that it doesn't affect the strong interactions or the weak interactions or the mega interactions. Therefore, it affects only gravity. The generations just differ in their masses. So the operator that changes generation has to be intimately related to the operators that enter into gravity. That can't be my idea, it's so obvious. Thank you. My wife thanks you. And so I'll come back to this when I show you the seed of gravity. So here are some examples of Siegel simplification. Special relativity is one, quantum theory is another. Neither of these are complete. They both require further simplifications, and Siegel worked on both. Wigner has this theory of group deformation, which he quickly published as soon as Siegel's paper came out. He'd been working on it for years, but he focused mainly on relativity. In his paper, there's no reference to the fact that the same process happens in quantum theory. I think this is because Wigner didn't believe quantum theory. He didn't think it would last. He thought what we needed was a theory of how consciousness collapses the wave function. In other words, he didn't accept the operation of quantum theory of Heisenberg. He clung to the de Broglie-Schrödinger school of the ontic wave function. Deep down, he hoped there really were waves running around the hydrogen atom, influenced by our minds. I forgot to mention, there is a connection between me and Eddington and Wheeler, quite concrete one. Namely, it was in the book of Mr. Thorne and Wheeler that I first learned that the metric I had worked out to describe the gravitational field of a concentrated spherical source had earlier been discovered by Eddington in his work on Whitehead relativity. I can't tell you how thrilled I was to learn that Eddington had thought in the same general area that I had. And now I think we're linked forever. The Eddington Finkelstein metric. It's such a ridiculous name. It's his metric. And that raised the puzzle of why he didn't discover the black hole. Because he certainly knew the problem of getting through the singularity. He had argued so vehemently with Chandrasekhar just about that question. And here he had the answer to it in his fingers. Why didn't he take the next step? That's a subject for an entire investigation and speculation that I won't try to carry out here. So now I want to show, this goes one step beyond Yang. Capital L represents the generators of the Yang group, SO51, let's say, or SO33, works just as well. We're going to freeze out two of the coordinates anyway, so we can't tell at this point whether they're time-like or space-like. And Yang went on and represented them by differential operators. Differential calculus is unstable. The commutator of x and d dx is 1, so the differential calculus is wrong. It's the singular limit of some finite structure, like polys. And so I've instead represented these angular momentum operators by spins. And this is just what Gert Feynman showed me when I stumbled into his office at Caltech in 1962 or something like that. He wrote down that X is a sum of a lot of gamma operators. And he was never able to write down a formula for P. You have to go to higher dimensions for that. You have to use the Yang group instead of the Lorentz group to have enough spin operators to represent both position and momentum. So I've done that here. And then I comes out as a component of angular momentum that you don't see in 4 dimensions. There's an extra 2 dimensions. And the transition to the usual I is a matter of getting all these spins lined up. The world is a little like a ferromagnet in respect to one component of angular momentum, corresponding to the magnetization direction for a ferromagnet. I'm glad I gave homage to Wheeler already. Here he comes again. The question is, what is the origin of dynamical law? I don't think this question is often asked in physics today. I think there's still a tendency, I know I practiced this for many years, until roughly 1994, thinking there had to be an a priori dynamical law, which is therefore very beautiful and simple and has few constants in it and so on. And the purpose of physics is to discover the law of nature. I think I learned this from Einstein. Before Einstein, I spoke of the laws of physics. And then after Einstein, I spoke of the law of physics. And now I don't think there's a law. I think there's the effect of the past on the future. And the only reason we got away with thinking there's an external law is that we looked at very little of the universe. I forget whether it was Sartre or Camus who said that hell is the other. Well, in physics, the law is the other. The law of the system is its entanglement with the environment, which is an enormously ordered quantum vector with huge off-diagonal long-range orders. And the quantum vectors represent portations into the system of quanta from the environment, which has this built-in order. The propagation from the past to the future is just teleportation, based on the entanglement of the elements outside, of the actions of creation and annihilation outside the physical system. Yes, time.
Fine.
Thank you. Maybe that's a reasonable point to stop. Let me see what I would have said if I had longer. Oh, the quantum theory, let me just finish that, it's so pretty. Where do you find the metric in all this? I mean the space-time metric. The important thing is that since Siegel, the dynamical variables form a Lie algebra. Every Lie algebra has a built-in metric, the killing form. You have to be blind not to consider the possibility that that is the origin of the metrical structure of the world. The killing form measures non-commutativity. So the metrical structure of the world would be counting microscopic non-commutativities. In Feynman's checkerboard game, it's the corners that determine the path length between two events. And in this game, it's non-commutativities. I think the ideas are related. So the killing form, however, is a number, a mere number, associated with two elements of the Lie algebra, like the angle between them. And the world is quantum. The gravitational field is presumably the classical limit of a quantum gravitational field. So we need an operator attached to each cell of the world. Well, the killing form is the trace of something. That trace is a quantum mechanical expectation value. So inside the killing form is the operator, which is the seed of the macroscopic gravitational field, according to this hypothesis. And here I've written it out This bold-faced delta means the difference between left multiplication and right multiplication, otherwise known as the adjoint representation. And then if you work out what this metric turns out to be, in the case of the n group, it turns out to be exactly the sum of the right metrics. Is the Minkowski metric for the space-time part, the Minkowski metric for the unity momentum, the usual metric for the angular momentum algebra, and even the right metric for the complex plane, which is where the magic number I lives. And the regularity, the non-singularity of the space-time metric closes back to Siegel's insistence that the Lie algebra of nature is regular, semi-simple. And I think that closure gives me the impression that I can continue on this track a little bit longer. Thank you.